Hello, my dear student. I'm Mr. Kitwala from Educators. I will be with you in physics for Form 5. And today, my dear student, we are going to proceed with our discussion about the topic of rotation of a liquid body for our subtopic of a torque of a rotating liquid body. This is where we are going to proceed for our today discussion. So let us make a link for the previous lesson. So on the previous discussion, we tried to see how can we get the linear moment, how can we get the linear acceleration. And we say that linear acceleration must be obtained by taking the mr square g sin theta, we divide by the moment of inertia through the center, then we add by mr square. And simply we tried to simplify in terms of the dimensionless coefficient, and we say that a which represented the linear acceleration must be equal to g sin theta, we divide by 1 plus c. That is what we tried to see on the last session. So for our today discussion here, we are going to see some examples related with the previous lesson or for the previous discussion. And our example we have here, our example number 16 for our first topic. So our example, as we try to see, say that determine the order in which a solid sphere, a disk, a solid cylinder arrive at the bottom of an inclined plane if they are all released at the same time to roll down the inclined plane, which is elevated at an angle theta. So as we try to see our equation, our example here, our example consists is explaining about the inclined plane. Now on that inclined plane, we was having the three liquid body. The first one was the solid cylinder, and the second was a disk. Also finally was a solid sphere. All of this, my dear student, was allocated at the top of the inclined plane. And then after being placed at the top of the inclined plane, they are being released together at the same time toward released together at the same time down toward the bottom. They are trying to rotate on that inclined plane. So but the inclined plane forming an angle theta. Now we are supposed to identify which amount of this liquid body could arrive faster than the other, even if they are being displaced or released at the same time. This is what we have been asked on our discussion here. So as we see our discussion here, that how can we solve this question? How can we identify the liquid body that can arrive fastly at the ground compared with the other? We get this one. Let us find the solution by determining the linear acceleration. Kwa ili tuweze kutambua ile liquid body iliyoweza kufika chini kwa haraka zaidi kuliko zile zingine, ni lazima tuweze calculate. We are supposed to identify the linear acceleration. So we need to substitute the respective value of c for each of this one. First of all, we are supposed to know the dimensionless, to know the dimensionless coefficient of that liquid body. And on the previous period, we tried to see that the dimensionless coefficient of the solid sphere, which is represented by C is equal to 2 divided by 5, while for this disk is half, and finally for this solid cylinder is a half. Now, after identifying this dimensionless coefficient, we were supposed to go and substitute this value for the formula of the linear acceleration, which is said that the linear acceleration is equal to g sine theta. We divide by 1 plus c. Now the value of c we have here. So using the value in equation number 4.90, we find the linear acceleration. Now we were supposed, my dear student, to go for our 90 for our equation 90 for our fourth topic, which give us the formula of the linear acceleration, and that is to say that for the sphere, let us start for the sphere to identify it is a linear acceleration. Now, for the sphere, my dear student, the acceleration of the sphere must be equals to g, then times sine theta. We are divided by 1 plus c, but the value of c we have, which is 2 divided by 5. Now we can substitute equals to 2.5. And after substituting it, my dear student, if we simplify, we get that the linear acceleration must be equals to g must be equals to 5 divided by 7 times the g sine theta. Now this is the linear acceleration for the solid sphere that it could take so as to arrive at the bottom. So after that one, let us go and look for the disk. The same formula we can apply by saying that the acceleration of the disk must be equals to the g sine theta. We divide by 1 plus c, but the value of c we have, which is a half. Now if we substitute, we could get that the linear acceleration of the disk must be equals to 2 divided by 3 times g sine theta. This will be the linear acceleration on which that disk take when is at the top of when it is released from the top and attain toward the bottoms. Finally, let us see again for the cylinder. Let us go and look for the cylinder. The same formula we can apply the formula number 90 by saying that for the cylinder. Now let us stem that the linear acceleration of the cylinder, my dear student, must be equal to g sine theta. Then we divide it by 1 plus c, but the value of c is a half. Now if we simplify, we get that the linear acceleration must be equals to 2 divided by 3 times the g sine theta. This is how you can find the acceleration, the linear acceleration of the cylinder. So after this one, we are supposed to say that since the sphere has a great linear acceleration compared by this disk, which is equal to cylinder. Now the sphere will have the greatest acceleration. They will arrive first at the bottom. Will arrive at the bottom first, because we tried after finding the linear acceleration, and we observed that the solid sphere contain the linear acceleration which is greater than that of the cylinder and also of the disk. Now we can conclude by saying that this sphere, my dear student, could arrive firstly at the bottom than the cylinder and also the disc. This is how we can answer this question. So the disc and the cylinder have the same acceleration. As we tried to see that, we observed that the cylinder and also the disc having the same acceleration, so they can arrive at the bottom simultaneously. Hizi zote hizi cylinder pamoja na huyu disc, kwa sababu na wana acceleration sawa, hawa watafika at the bottom kwa pamoja zaidi ukilinganisha na ile sphere ambayo itatangulia kufika. Kwa hiyo tutaconclude kwamba huyu sphere atafika at the bottom firstly ukilinganisha na zile zingine. So after there, let us look for another example, which is our example number 4.17, as we observe here, my dear students.